Okay, so before the coffee break, we ended before the coffee break with the notion that the inverse of the matrix is apparently the transpose, or in other words, the transpose times the matrix itself gives the identities. That is an interesting thing, because you could also read this as constraint equations, right? I mean, you can read it like, okay, R transpose times R minus the identities is a lot of zeros. So how many zeros do we have? No. 9 zeros. It's a 3 by 3 matrix, right? So 3 by 3 is 9 zeros. Meaning we have apparently 9 constraints on the rotation matrix. So we have 9 constraints on the entries of R. How many entries do we have?
9.
Yeah, and we have 9 entries. Meaning how many rotation matrices are there then?
1.
Only one, eh? That feels a bit strange. I mean, so there's only one matrix, and that is the rotation matrix, and then you're in business. Yeah, looks simple. Well, if you look closely, then these 9 constraints are not all unique. Because, I think the easiest way is to say that R transpose times R, if I do the transpose, that is also equal to R transpose R. So all the entries which I find in this expression, if I have a number, I have 1, 2, 3, 4, 5, 6, 7, 8, 9. This number is identical to this one. And this number is identical to this one. So all these off-diagonal things, or in other words, the thing is symmetric. So if the thing is symmetric, then that means, then I only have 1, 2, 3, 4, 5, 6. So I have only 6 independent constraints on R. And then 9 minus 6, meaning I have 3 free parameters, or free parameters to write R. And of course, what are these free parameters? Yeah. For instance, 3 angles. Which angles? Well, about the x-axis, the y-axis, and the z-axis, right? Super simple. Well, it turns out that that's not completely true. Because so you would think, the x-axis and the y-axis and the z-axis. I have 3 axes, so I have 3 rotations. Okay, let's go to the 2-dimensional case. How does it work there? I have a rotation matrix which is 2 by 2, meaning I have 4 entries, right? 4 things. And then R transpose times R is the identity, is one is the identity, meaning I have 1, 2, 3. I have 3 constraints. Yeah? Meaning I have 4 minus 3 is 1, one angle. Well, that sounds about right. Because I have 2 axes, x and y, and then orientation we say, oh yeah, there's this other coordinate system, x prime, y prime, and then I have this angle phi. So the math is okay. And if we think what was the rotation matrix, well, if I do it by head, I always make errors, but it's something like this. Nice way, parameterized with 1 parameter, that's a rotation matrix. By the way, you can easily see now also that the transpose is equal to the inverse. You can easily see that on this simple 2 by 2 problem. Okay, now here we would say the 3 angles about the 3 axes. Let's go to the 4-dimensional world. And then we have the axes x, y, z, and t, for instance. Our parallel universe. The rotation matrix in a 4-dimensional world is 4 by 4, and that are 16 entries, right? Then the R transpose times R is identity R 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 constraints. Meaning in the 4-dimensional world we have 16 minus 10 is 6 rotation parameters to describe this rotation matrix. Whereas we have 4 axes. So your reasoning about, oh, we have 3 axes, so we have 3 rotations, is false. That is incorrect. Apparently rotation has to do with something else. And one way to look at it is rotation is about an axis. So let's, for instance, take the simple 2-dimensional case. Then all the rotations are about the z-axis. This vertical axis, this guy here. And how do we build that vertical axis? Well, we have these 2 axes, and then they build a plane. And then all the rotations are in that plane. And you can build a normal vector to that plane, and all the rotations are then about that normal vector in that plane. The same you can do in a 3-dimensional world. You can take 2 axes, and then you construct a plane, and then you have rotation about that one. And then you can take 2 other axes, another plane, and 2 other axes, the third plane. You cannot construct more independent planes. 3 planes, 3 rotations. And now if we go to the 4-dimensional world, how many planes can you construct? Well, 1 plane, 2 planes, 3 planes, 4 planes, 5. Exactly, 6 planes you can make by combining always 2 vectors. So rotation is about an axis in a plane. That is how it usually works. Okay, back to our 3-dimensional world. So the 2-dimensional world was clear. We had that example. By the way, how did I get this rotation matrix? I now did it by head, but we could also take the whole definition of the thing. So in a 2-dimensional world, I could also say, oh yeah, I have my base vectors here, E1 and E2. And then here I have in a rotated configuration the other, E1 prime and E2 prime, and this is the angle phi. Then the expression of E1 prime in this coordinate system is, of course, well, it's a unit vector, so I have the cosine phi here, and for the vertical component I have the sine phi. And the E2 prime is, so this vector, I have a minus sine phi, and in the y direction I have cosine phi. And now, constructing the rotation matrix Rij is actually super simple, because by definition it was the dot product of this guy and the prime guy. So let's do it. So if we take this first entry here is the E1, so that's the 1, 0, dot product with the with this one, the cosine phi, sine phi thing. That's the first entry. Then the second entry here is again this 1, 0 dot product with this vector, and the minus sine phi, cosine phi. And this one is 0, 1 with this same guy, not a phi, and the last one is 0, 1 with this guy. And here we see all these unique dot products we can do in a two-dimensional world. And ergo, what do we get? Well, we get a cosine phi here. This we get a minus sine phi. Here we get a sine phi. And for this guy we get a cosine phi. And that clearly demonstrates how it works. And of course, if you want to have the inverse, well, you do the dot products the other way around, and we already know we get the transpose. Okay, so that was a two-dimensional world. We now have a little bit idea how that works. How does it work in a three-dimensional world? Okay, we have three parameters, and for now there's one guy who came up with a system, and his name was Euler, of course. And we use what we here call Euler angles. I mean, there are other ways to do that, and I will talk about that in 2 weeks, but for now we take a three parameters Euler angles. Now, Euler angles is a recipe. And I always say it's like baking a cake. Meaning that the order is very important. And what do I mean with the order? Well, let's bake a cake, right? So if you want to bake a cake, well, what does a cake look like? So something like this, right? And then a nice cake out of the oven. So how does that work to bake a cake? Usually there is like it breaks open at the top. Something like this. Okay, what do you need for a cake? You need an oven, you need a form to put the cake in, you need flour, you need sugar, you need butter, and something to mix it, right? Now, with all these ingredients, you can have various orders. Like you can put all the flour and the butter and the sugar in the oven, and then light the oven, and then when it's done you put everything in the form. That's probably not going to work. And so it is very important to have the right order. Light the stove, let it heat up, first take the flour, then cut the butter in that, put the sugar, make it a little bit cool, and then put it in, etc., etc. So there is an order, and the same with the Euler angle. So what is the order? You start with aligning. Oh, that is not aligning. It's still not aligning. Align the body fixed frame, and we usually call that with a B. To the space fixed frame, N. So first you align up every stuff. You take your system, you say, okay, we align it up. Well, what are the axes? These are the axes, and this is my system. Okay, with two different hands, I cannot do that, of course, but you align them. And then the first step you do is so this was actually step 0, right? And then the first step is you rotate an angle phi about the z-axis. Okay. Then the second step you do is you rotate an angle theta about, and now I should be clear, the rotated x-axis. Because by the first step, you have changed, you rotate about the z-axis, and apparently then the x-axis changes. But then we rotate about the rotated x-axis. And the third step is that we rotate an angle, and I always forget which one, psi, about the rotated, and a lot of O's to indicate, we have now two rotations. And which axis do we take? The z-axis. Now that is a little bit surprising, because I would say I had z, x, and why is there not a y then? This is Euler. And Euler is pretty smart, so I'm not going to outsmart him. So apparently this is how it goes. Now, we are engineers and we like to visualize stuff. So we like to draw pictures with this. Now, a long time ago, I spent a sabbatical year in the US at Cornell University. And I'm proud to say that my contribution to Cornell University in that year is one picture. And I'm pretty proud of that. It's one picture. And the picture is they call it cans in series. Cans in series. Okay. I'm happy with that. So what is the picture? Well, if you usually look into a book about rotation, they say, well, we have this coordinate system, and then we rotate about, the z-axis, that's clear, and then we get this axis, and then we rotate about this axis an angle, and then, we get this one, and then finally we rotate about this axis, and then we get this coordinate system. Maybe the lines are a bit more straight, but in essence that is the thing. And I have no clue. I never understand these pictures. I have so hard a time to understand them. So that doesn't work, right? That doesn't work. It's like this video game. This doesn't work. This doesn't work. Well, this doesn't work. So what do? We make an exploded view. That was my thing. So, and how do we make an exploded view? Well, we draw this coordinate system. This initially this base system, and what did I call it? X, Y, and Z. So this is my inertial frame here. And then if we say we rotate about the z-axis, then we just draw this thing, like a real hinge, or what they then call in the US a cans. Yeah, I don't know. It's a can. I don't know why they call it a can. Anyway, and this is fixed to the ground. So that is the first rotation. And then remember, the second rotation was a coordinate system which was at the end, because things should have happened about these axes, the rotated x-axis, and that was about that axis. So again, we draw a can. And then you would say, well, yeah, but these points should coincide because it's all the same origin. Immaterial. It's an exploded view to understand how the thing works. And then finally, the last rotation was again about the z-axis, but now attached here, so around this one, so here. And then here we have, at the end point here, we have this body fixed frame with the x prime, y prime, and the z prime. And if we then do it a little bit nicer and with hidden lines and so on, I don't know. Then, and we put symbols to it, then the first rotation was a phi, the second rotation was this, was a theta, and the third rotation was this psi. And now we have a clear view of what happens. We can see, oh yeah, this is this succession of cans in series, a succession of rotations. And if you look at the picture, the order is apparently important, because if you change the order of the two, you get two cans in the z direction and one in the x. It's not going to work probably. This doesn't work. This doesn't work. So now how do we find the rotation matrix for this system, where we parameterize with phi, theta and psi? Well, what did Napoleon always say? My stomach hurts, yeah, that was what it. And the other thing? What was the secret to his success? Divide and conquer. So divide and conquer. So again, we are going to use our scissors in a way, and we're going to look at all these individual rotations, and then we can combine them to one rotation. So the individual rotation, so the first one we have to look at is, well, if we have just a rotation about the z-axis, so these x, y and z, we have this angle phi, and attached to that is this other coordinate system, x prime, y prime, and then there's here z prime. And then we want to know what is the step from one to the other. Now I want to reserve primes for the last one, so I'm going to cheat a little bit and think a little bit ahead, like Napoleon did with his divide and conquer. So instead of prime, I'm going to make 3 primes here. Doesn't really matter, just to distinguish. And then I want to say I want from this rotated back to the world. That is my transformation. So I want to know how do I get here and a rotation matrix, and then here we have phi. And then, sorry, I make a mistake. Other way around, of course. Cool. I want to go from my local system to my inertial system. So I want to read back. Then what is this rotation matrix? Well, it is the one we already had developed for planar rotation, right? We already did that. There was a rotation about the z-axis with the x and the y and the phi. So that matrix R theta is very simple. With the z-axis nothing happens, plus that the z has no contribution. So we can write for the z all zeros here and zeros and a 1. And we only have to fill in the xy part, and the xy part is identical to the one in the two-dimensional world. So we have cosine phi minus sine phi, cosine phi. Okay, so that is super simple. Then the next step is, now we start from here, and then we say, well, we want to do a rotation about the x-axis. So then our sort of inertial, or our base system, is this thing with the 3 primes, right? And then this is the z with the 3 primes. And then the rotation we have is about this axis, the x-axis. And then the frame I put here, I identify, of course, with 2, x double prime, z double prime, and y double prime. And the rotation was theta. So now we have to do a little bit thinking for this rotation about the x-axis. You can draw pictures for that, or well, first let us write down what we want to have. So the base frame is this 3 primes, then we have a rotation matrix in theta, and then the local frame is this 2 primes. Now what does that look like, the r theta? Of course we have to then draw a projection, and the projection is actually already here. If you look along this axis, and then you see, oh yeah, it rotates like that. Okay. So which axis is invariant? Well, that's the x-axis, of course. So nothing happens with that one, and it has no contribution. Then we know from on the diagonal there's always the cosine of theta. And then the only thing we have to place is a sine theta, and the big question is where does it has to be? Well, we can read this as x, y. The rotation is in that direction. We can read this as x, y. So the order didn't change. So it's just minus sinus, and here sinus theta. And actually, these are the only things we need, because finally, when we come at the last rotation, then this is the base frame with these double primes. So we have x double, y double, z double, and then again the rotation was about the z-axis. It's the rotated z-axis, but it doesn't matter. You have z, and the symbol which you went by that was psi. And then at the end, now finally we have here our body fixed frame x prime, y prime, z prime, and the name which goes by that is b. So the mapping we want to do is we want to express everything in this x double dot. The rotation matrix is psi, and then here we have the triples. Then how does it look? Well, it is a rotation about the z-axis. So that's super simple. Again, 0, 0, 1, 0, 0. Only now the thing is psi instead of phi. So we have cosine psi, and here the minus sine psi and sine psi. Oh yeah, sorry. Yeah, a little bit too much primes. Thank you. Let's throw away all the primes and start afresh. Thank you. So from these doubles, yeah. The other way around. Yeah. Yeah. From the local, I want to go to this global one. From the local, I want to go to this global. Yeah. So now I have all these separate parts, and I can substitute this one. So this I substitute in this one, and then this one in the previous one we had before. So finally I can get my x in the global frame, and then my x prime in the body fixed frame, and then the order is apparently the r of the psi times the r of the theta times the r of the phi. Or in other words, our rotation matrix. And now, yeah, it's nice to use these symbols, this way. Our N, R, B is apparently rotation matrix phi times rotation matrix theta times rotation matrix psi. Okay. All very nice. If you then write out the expressions, it's a triple product of cosines and sines. So if you write out all these matrices, and I'm not going to do it here, then you will see you have at the most triple products of cosines and sines, and also double and single. Now note that there is an order in here, and if we have matrices, for matrices we know that A times B is not equal to B times A. Although it's for scalars, true, it's not for matrices. And you could also say, in another word, if I see these three angles as sort of vectors, you would say, I have a vector with a phi, and I have a vector with a theta, and I have a vector with a psi. They're not equal to starting with the vector theta and then adding the vector phi and then adding the vector psi. This whole addition thing doesn't hold. Or in other words, Euler angles are no vectors. And to demonstrate that, I like to do a demonstration with some volunteers. And as it happens, I have a lot of volunteers here in the room, so I propose we all volunteer. And the experiment is as follows. Experiment is as follows. You are sitting in the room here, and the easiest way to draw that is, let me look, if you are sitting there, so you have a head, and you have a nose, and eyes, and ears, right? Something like that. Then your coordinate system is the following. The x is forward, the z is up, and if that is the case, then the y is to your left. This is your y. And now let's assume that is how it works in math. If you want to prove something, that something is not true, you say, let's say it's true. Assume they are vectors. So assume these Euler angles are vectors. And then I have one vector, one Euler angle vector. So I say this Euler angle vector is, and I just order them. The first I call phi, the second psi. No, that was not true. The second was theta. Theta. And the last one is psi. That's how I call my Euler. So then V1, the first rotation, what did I do? Minus 90, and everything is in degrees here, 0, 0. So very simple rotation about, well, the first one was the z-axis, so a minus 90 degrees, super simple. And then the second rotation is I should take something different, of course, and then I took 90 degrees 0. So if this is your x-axis, then 90 degrees is like this, right? Yeah, okay. And then I'm going to divide the audience into two groups, and that's super simple. That is group 1 and that is group 2. And what was 1? That was 1, yeah. So 1 is going to do V1 plus V2, and group 2 is going to do V2 plus V1. I mean, and let's see, if they are vectors, then we should be in the same configuration, right? And if they're not, then okay. You or what? So minus 9 plus cx. Van de x-as dat je hebt. En dan blijf staan. Oké, nou jullie. Wij moeten nou eerst 90 graden op onze x-as. En dan min 90 op de z-as. Zoiets? Oké, blijf staan. Ik moet even een foto van jullie maken. Mag dat? Wie niet wil, moet maar laten zeggen dat het niet wil. Dankjewel. Mijn foto laat zien dat jullie niet allemaal dezelfde kant op staan. So, this is a simple proof, actually, just a very super simple proof, which I hope you will never forget in your life, that these Euler angles are no vectors. So, you cannot add them up. The order is apparently important. How you do that, like we've written down here, this order is very important. If you mix up the order, you get a totally different thing. That's not a problem, but it's just something to note, to understand. Then finally, of course, as we've seen in the equations of motion of Euler, the angles are not present, but the angular velocities and the angular accelerations. So we now have to make the connection between these Euler angles and angular speed and angular acceleration. So then again, we start with our potato thing, and again, I'm not so interested in the position of the center. So, but let's draw it. We have the inertial frame here, and we have our body frame here, and we have this point P here, and yeah, I could say this is the vector P with respect to C, right? And this is the vector, not the vector, this is the vector C, and then finally this is in our whole system the position of point P. Or in other words, we say, how do we get at point P? Well, we go to the center of mass, and then we have P with respect to C. Now, This is just coordinate free, of course. We have, and if we want to draw it say it in components, we say, well, we want to know the position in the inertial frame, that is this guy in the inertial frame, plus this guy expressed in the inertial frame. Now we really have numbers which we can use in MATLAB. But remember that we can also, of course, this relative position, we can also write it as this vector expressed in the body frame, right? And the nice thing of that is these are constant, these numbers, the coordinates are constant. But then what do we need? Then we need this rotation matrix. So that is the way how we go about to finally express our position in space. Now, I'm not so interested in all this translational part. I'm really interested in this part. So you could say I'm really interested in this part. P with respect to C is this rotation matrix. P with the B of C. And for the translation, I'm not so interested. But before we do that, we have to look at speed. So the speed. So what is the speed of point P? Well, it's the speed of C, of course, but now we have two components here. We have the rotation matrix, times this one, B with plus the rotation matrix itself, times the time derivative of this guy. And now you understand why I love to have these numbers here, because this is of course always 0. Because these numbers are constant, so this term is irrelevant. So the speed now of the body of point P is now the speed of the center of mass plus, and this is really the speed due to rotation. Due to rotation. And we focus on that one. So this is, I'm not interested in that at the moment. So apparently the r dot of P with respect to C, expressed in some coordinate system, is this r dot of this rotation matrix times this vector r B. So this expresses rotational speed. Now there is one problem with this one, is that this vector is expressed in components in the body fixed frame, and this is in components in the space fixed frame. And actually I want to have everything in one frame, because then I can write like a vector equation, right? Then I don't have to bother about any coordinate frame. I can do that because I can write this one in terms of the inertial frame. So I can write, okay, the speed of P with respect to C is this apparently this r dot B, and now I have to find a way to express, to transform these to these. Now we know of course what that is. That was our rotation matrix itself, not the time derivative, and then the inverse, and then we know also that for the inverse we need the transpose. So it was apparently this RBN transpose. So now I've written down the speed of this point is this matrix stuff times the speed, and everything is in the same coordinate system. So for simplicity now, or for shorthand, I could say, so this r dot apparently is equal to this r dot r transpose times r, because everything is in the same coordinate system. Question?
Why do you want the position vector be with respect to C in the inertial frame?
Because I finally want to make this step. Oh, in the inertial frame here, because Newton equation is, everything is in the inertial. Yeah, so everything is, here I want to have inertial frame. Why do I want to have this one in the inertial frame? Because I want to go back to a vector equation, a general vector equation. So I want to express everything in one coordinate system. And then I can say, oh yeah, forget about the index of the n. It can be any frame. So then we drop the n, and then we're stuck with this vector equation. That's why I want to go back to one reference frame. So either everything in the space fixed or everything in the body. Yep. So now I have this general vector equation. R dot is R capital R dot R transpose times R. But if you look at this matrix, it rings a bell, at least with me, because remember R times R transpose is the identity, right? So how do we get from here to there? Well, if I differentiate this, I get this R dot R transpose. So if I differentiate, I get R, but I get more. R dot is 0. But this looks a lot like this. If I say, for instance, this R dot R transpose I call W, then R dot transpose is W transpose, right? Just a transpose of the thing. Or in other words, what is stated here is W plus W transpose is 0. And W is a sum matrix, so we get R dot is apparently W times R. Yeah? And this W with this thing, if W plus W is 0, then apparently the matrix W is equal to minus W transpose. Well, which matrix complies with that? Well, if something should be the negative of the transpose, then on the diagonal we can have zip, because a minus 1 is never equal to plus 1. There's only one number where minus and plus are identical, and that number is 0. So we have zeros on the diagonal. And then everything which we have here, we have minus here. So if we have, for instance, an A here, then I have a minus A here. And if I have a B here, then I have a minus B here. And if I have a C here, I have a minus C here. Now, if you look at this, this looks a lot like the cross product. And that is actually true. If we now define our R dot R transpose, which we know is this strange matrix with all those zeros, and if we define it like this, we say we call this omega 1, we call this omega 2, and we call this entry omega 3. Only 3 entries, right? And then apparently this is minus omega, this is minus omega 2, and this is minus omega 3. It's just a way. I mean, I could also say A, B, C, but then it was less clear. I use these 3 things. Then I can, with these 3 components, I can write in a vector form. I can write R dot is W times R. I can write as omega cross R. So now we see that, oh, this is the one we know from our kinematics, that if we have a rotational thing going on, then, and there is no, the thing is not becoming larger or smaller, then the speed is this angular speed cross product with this R. So you could say this is the definition of angular speed. Is R dot R transpose. Finally, we have a nice way of writing this matrix. You could also write it with a tilde. I do it like that. And then what do we mean with omega tilde? That is this matrix. Omega 1, omega 2, omega 3. Well, that's also explained in the book. So then you have a nice matrix vector. This is a matrix. And that matrix vector representation is handy because cross product is such an anomaly in your whole derivations, whereas matrix vector products are standard things which you can easily work around. Especially if you have multiple cross products, you have no clue what is going on. But if you have representation in matrix form, the product of 2 matrices you know. So this is very handy when you want to find out what is the effect of omega cross cross R. What is that? You say, well, I'm going to write it like this, omega tilde times R. And if you do this matrix multiplication, yeah, then you immediately see, oh, that is the thing which comes up in the mass moment of inertia with x squared plus y squared, and off diagonal terms are 1 times 2 and 3 times 1. And so that is just a handy way of writing. Back to our definition, R dot R transpose is this omega tilde matrix. The final step we now have to make is, of course, we have this guy is in Euler angles, and this guy is our angular speed. And we have to find the relation between the time derivatives of the Euler angles and the angular speeds. So how do we do that? Well, we just differentiate. So what is R dot? Well, that is dr, and the first angle was phi dot times R transpose. Then the second one is theta times theta dot R transpose. And the third one is psi dot R transpose, is apparently this omega tilde matrix. Now, this is finding out then the relation between theta dot, phi dot, theta dot, psi dot, and also the angles and omega. The angles also come into play because they are here. That's a lot of work. Now, if you have time and energy, you can do that. Expanding this. I mean, these were triple products, remember, so these are double products, but then again you get quintal products, the most 5. Becomes very complex, where in the end, you know, there is a linear relation. I mean, here we have linear omega, here we have linear phi dot. So we should be able, in the end, to write something like this, like, something phi dot, theta dot, psi dot, although there are no vectors. And I repeat, there are no vectors. But we can write this mapping, omega 1, omega 2, omega 3. And then the entries here are cosines and sines and all those kind of things. You can extract that from here. But there's also an intuitive way, and that again goes with these cans in series, of course. And you just make the picture. You draw the picture. You say, oh yeah, I have this first can, and then I have this second can, and then I have the last can. And then here I have my body frame. And here I have my inertial frame. And then we know that the rotation about this one was phi, so apparently you could say there is a vector here, a omega phi, and that has the components 0, 0, phi dot. Phi dot. Clearly a rotation about the z-axis. And same way here, I mean, we can say, oh, there is a vector here, and that is, what was it, theta, this guy, omega theta, and it had components expressed in some coordinate system, but in this coordinate system, the component is around the x, right? Phi dot 0, 0. And likewise here, the last one, this is also a omega about some direction, and it's psi, and in some coordinate system, the components are 0, 0, and psi dot. Of course, all these are in different coordinate systems. These components are in the inertial frame. So if I write down my omega, I can immediately say, oh, it's the first one. That's the omega phi. That's correct. That's in the inertial frame. Plus, and then I would like to put this one in, this omega theta, but there is a problem that's in another frame. That's not in the inertial frame, but it's in this frame. But I know how to transform that back, right? There's only one rotation matrix in play. And the rotation matrix is about this axis. So I put here the R of phi. Then I rotate that back. And then finally, I can say, oh, I can do the same with this guy, with this omega psi. And I have to first rotate it with respect to the theta, and then have to rotate it with respect to the phi. And if I do it like this, it becomes a lot easier. then I get component-wise, I can say 0, 0, psi dot. Then I have to write down this matrix, but that's very simple with cosines and sines. There was a theta dot here and a 0, 0. And then the product of these two matrices, it's a bit more complex, but still, it's not as much work as we had above. And that was psi dot. Now the outcome is of course super interesting. So let me, 100, let me write that down, what the final result is then. Then omega x, omega y, omega z is, and then we get a matrix set times, and the order I took is phi dot, theta dot, psi dot, but there are no vectors. Yeah. But what are the entries? 0, 0, 1, cosine phi, sine phi, 0, and then sine phi, sine theta, minus cosine phi, sine theta, and my guess is cosine phi, theta. Yeah, and that's it. So now we found the relation between the time derivative of our Euler angles and our angular speeds. Of course, you can transform the thing to a body fixed frame. You can also write them in a body fixed frame. We know how to transform them, and you get sort-like expressions. You can do it with a rotation matrix again. It's quicker by drawing the picture and say, oh, I transform everything to this coordinate system. That's a lot easier. Now, why are we doing all this? Well, because we use for orientation, we use these angles. But from our equation of motion, which is some torque is I omega dot plus omega cross I omega, we solve our omega and omega dot and omega. So we have to find a way to update our Euler angles. And how do we do that? Well, then we need a differential equation. So we need to know what are our time derivatives. What function are they as a function of these angles, phi, theta, and psi, times these omegas, omega x, omega y, omega a. And that is actually given by this one. So this set of differential equations, here we solve our angular acceleration, and from these set of differential equations we just map our state, our angular speeds, to our time derivatives of the Euler angles, and then we can integrate these with time, and we can integrate these with time. So meaning that the state of the system, if we want to write what is the rotational state of our system, then we say, oh yeah, it is the attitude, phi, theta, psi, and it is these three angular speeds. And our state equations, well, the first set of state equations are these, and the second set of state equations are these. And by that we can then just integrate and resolve and find a new orientation of a body. Okay, sorry for the delay. Next week we have a session day, Hemelvaartdag, so time off. So I see you in 2 weeks. The schedule for the homework is just as is. 1 week this, 1 week that.